All right. Do you see my screen?
Yes, I can see it perfectly.
Hey, so we are starting. I want to start with some information about me. Basically, my name is Artyom Arakcheyev. I'm a doctor of business administration, a master in computer science, and actually I have 4 university degrees in total and more than 200 certificates. So most years in my career, I was working as a software engineer. So I learned about 18 programming languages for kind of artificial intelligence, full stack, embedded systems, cloud solutions, and almost all kind of computer software. And now I'm transitioning to the quantum computing. Also, I have some entrepreneurial experience. I won some kind of new venture challenges, hackathons, and um, kind of tried to kind of launch some businesses. So this is some information about me. By the way,
Okay.
I would like it to be something like a dialogue. So if you kind of have any questions, feel free to interrupt me and ask something like at any moment.
Okay, I'll do. If I have any questions, for sure, I'll let you know.
I appreciate it. So I currently study in this quantum computing program. It's made by Womanium. It's basically an organization that kind of educate young women, kind of including like entrepreneurial and STEM. And they also actually they not only educate women but kind of everyone actually. And now they have this program for quantum computing, and the program is great. So they cover so many topics in quantum computing, quantum sensing, quantum applications, algorithms, and they have kind of many speakers. So it's kind of more than 50 speakers, as you can see on your screen. So it goes very well. And kind of to earn a certificate in this program, I do the quantum kind of education. So I just kind of meet people who are interested in learning more about quantum and give them kind of some information. So and then also kind of last year I studied at MIT with kind of quantum computing program. So kind of those professors are very well known in the quantum industry. So also kind of some knowledge comes from there. On this screen, I would like to show you kind of how much money different countries invest in quantum computing, because there is a kind of race between different countries who can create a sufficiently powerful quantum computer, and that country could kind of get all the information, like maybe like secret services of that country could get kind of all the information, because kind of Shor algorithm would allow to decrypt all information, and the information is like a new oil. So you can see that kind of the China invested the most. They invested about $15 billion. Then kind of United States and Canada, they invested about $1 billion. Kind of some countries invest, kind of Germany invested three billions. My country, where I was born in, Russia, invested kind of a little bit more than $500 million. So kind of in total, kind of all the world effort, about 30 billion. That is kind of a huge amount of investment. Here I would like to show you the quick lab tour to the Google campus for quantum artificial intelligence. So they have kind of nice presentation here for kind of, they start with our planet, and then we move towards the kind of campus in Santa Barbara when they develop quantum hardware, software, and kind of various quantum algorithms. So it is here. So they collaborate with kind of many other labs and organizations around the world. And then we move to this place, kind of looks nice. And this is where the actual laboratory is located. So here is their building, Google Quantum AI, and then this is how the laboratory looks like. It's like a big laboratory, and at the center you can see actual quantum computer. You can see kind of so many connections come to it, and in the center there is a dilution refrigerator with very cold temperature. It's temperature of about absolute zero. It's kind of minus kind of 10 millikelvin, or almost minus 273 degrees of Celsius. So like super cold, but only this temperature makes the quantum computing possible. Let's come a little bit closer. This is kind of how it looks inside. So this metallic construction is partially made of gold, and then you can see a lot of communications coming to the quantum processor. The quantum processor is kind of a very small device, actually. So here it is a quantum processor. There is like a lot of communications come to this, and then as you can see, so it's about like 150 square millimeters. That is kind of size less than a coin. And yeah, here we come closer. And if we could look on this quantum processor under the microscope, then we could see kind of qubits. The qubits is what makes the quantum computing possible. So instead of bits, they actually use qubits. So as you can know, in the kind of computer science, so we code all the information with zeros and ones. So kind of all the music that you can listen, all the videos that you can watch, the text that you read, everything is encoded as zeros and ones. And basically these structures allow us to create something better than zeros and ones. And this allows us to create a qubit that can be not only in position of 0 or 1, but also kind of in something between zeros and ones. And this is
actually what I understand about the quantum computing is that is exactly what is that what you're telling is that okay, traditional computers works by bits, no 1 and 0s, it's open and close or on off. And this is basically it can be quantum computer is like it can be 1 or 0 or any of the states in between 1 and 0.
Correct.
So
correct. It can be some state with probability to be measured like 1 or 0. Like could be like, for example, if the value of qubit, we come to this very soon. Actually, let's jump there kind of right away since we talk about it. So kind of the classical bit, only 0 or 1 is like a switch. There is electricity or there is no electricity. And this qubit is like a sphere, and the value of qubit is kind of some value on top of the sphere. So you can see here is kind of some point on the surface. And then we see that this point is closer to 1 and further from the 0. So if we measure this qubit, then it has more chance to be 1 than 0, but also kind of there is some probability that it can be measured as a 0.
So the qubit is measured in a three-dimensional space as well. It's not a bit dimensional.
Yes, it's kind of it can be in three-dimensional space. The value of qubit can be on any point on the surface of the sphere. So it can be on equator, kind of can be on kind of on top. Then if it's on top, it can be 100% probability that it will be measured as one, or it can be on bottom. Then it can be 100 probability that it will be measured on as a zero. So it's basically a probabilistic concept. And then we can kind of there is gates, so we can perform operations on the qubit. They allow to kind of move this value of qubit to kind of any almost any kind of position on the sphere. So yes.
Okay, let's continue. It's okay.
Okay, super cool. So this device, this what we see under the microscope, it's actually kind of hardware implementation of one qubit. It's made on superconductors, but there is kind of various competing technologies. So it can be made as trapped ion, or it can be made as kind of the photon, or there is like a various kind of competing modalities of the qubit, how it can be made. This is just one of the leading technologies. So the superconductors or kind of Josephson junctions, they are kind of they are super cool technologies. They are low to create very stable qubits. So this on this slide we can see the problem. Why do we need a quantum computing? Why don't we just kind of use classical computers as we always did? And the problem is because some kind of problems are not solvable on classical computers in some kind of realistic time. Like, for example, if we need to kind of compute some molecule, kind of design a new material, or kind of find the shortest path between kind of many cities, then this task could not take kind of minutes or hours or even days. Those kind of tasks could take like years, or maybe
thousands of years.
Thousands of years, or kind of millions of years sometimes. So it's kind of super long to wait kind of while we can compute it on a classical computer. At the same time, those kind of computations could be done super quickly, just in seconds, in quantum computers, because of the qubits, and because the way how the qubits works, how those quantum computing works. So here are some applications of quantum computings, and as you can see, there is a lot of various kind of applications and industries, including like logistics, marketing, climate, big data, manufacturing, decision making, chemistry, kind of cryptography, and many others, including the financial services. So there is kind of applications for portfolio management, for kind of creating an optimal portfolio. If like some company or some investor would have some portfolio of assets, that how he could know that he has kind of he maximized value with kind of minimizing the kind of price of that portfolio and risk of that portfolio. The kind of quantum computing is super good for solving those kind of problems. Also, like transportation, healthcare, telecom, aerospace, they all good. And kind of interesting fact that kind of the traveling salesman problem that are solvable on quantum computing, that is kind of it's difficult to solve on classical computer, but kind of there is bees and mushrooms who also can solve those kind of problems, and they kind of solve it super quickly. And basically, the quantum computing sometimes is closer to the nature than classical computers, because in nature there is no switches, there is no transistors, there is no like something like zeros and ones, and in the nature there is kind of, you know, on that subatomic levels there is kind of particles, there is kind of photons, electrons, and they all have those kind of probabilistic properties, and basically we use nature itself to make the computation. Like, to, for example, if you want to model some new drug or kind of some material, then it's easier to compute kind of structure of that molecule using the same kind of means. The kind of qubits are the same like those molecules or those kind of particles that we actually try to understand. So
Okay.
Now,
what I understand about quantum computing basically is that first of all, it's not like, of course, traditional computing is you need to set the instructions on what you need to get. Like, okay, you program them in order to get something that you already know what the answer is, but you don't know how to get the answer. And basically, you program them so you can set instructions to get into that place. In quantum computing, what I got by that is that you're going into the theoretical spectrum where you don't know what you can. You know that there's something there, but you don't know what exactly is there. So by the calculations, you can show you things that you don't specifically had to program, but basically you can get those results. Is that correct?
Yeah, it's correct. Basically, to kind of solve some problem on quantum computing, we need to have some data, and we need to kind of model those data using the kind of quantum algorithm. Basically, we need to kind of model the problem using those kind of qubits, and then we could solve this problem using quantum algorithms. Sometimes we know what is kind of problem we're solving. Sometimes we don't know what kind of problem we're solving. For example, if we just use some kind of regular algorithms, then we kind of do it pretty straightforward. But also we could use quantum machine learning, and then we don't know how the actual quantum computer would solve this problem. It's basically same for a classical computer. It's also how machine learning works on classical computers. It's basically a big question. We just know that it works, but what's going on inside of the neural network, it's a big question. And then kind of the quantum computing allows us to also to do the artificial intelligence. There is quantum AI, and there is quantum machine learning that allows us to have some input data and then kind of allow us to match the input data with the answers, and then that kind of quantum machine learning algorithm would learn how from the input data find out the answer for the problem or the solution. Does it make sense?
Yeah. I'm taking notes at the moment. Yeah.
Okay. So, super cool. So what I wanted to show you here is the financial industry also use quantum computers, and basically here you can see the kind of financial market. So some people are trading there, maybe some stocks or kind of some assets, and then quantum computers allow to kind of find out this kind of how they can build the optimal portfolios, and also they can build the quantum machine learning algorithms to predict the stock prices. So like it's always good to know what will be like a price kind of tomorrow or after tomorrow. And the quantum computing is also kind of good at solving those kind of things. And then also on this slide, I just kind of yesterday I found a paper. It was the paper was published by some people. One of them studied with me on this Womanium quantum computing program, so we met there. So he came up with a financial fraud detection, and he kind of his team analyzed some types of frauds and how the quantum computing can be applied to detect the fraud. So they came up with a quantum computing algorithm here, and then they found that they have a very good results with that. So they found that results of this algorithm are much better than for kind of any classical algorithm. So that quantum computer is able to detect the fraud kind of with very high probability of correct answer. So kind of
okay,
interesting paper. If you like, I can send you some materials.
Yeah, I will appreciate that. So I can get.
Super.
I can check them out.
Super cool. So here we already talk about the qubit. So it's kind of can be compared as a metaphor. We could take a look to the maps, and then we can find that our planet is like a qubit, and we are kind of, so like for example, I'm in Cancun right now, and this can be like my like value of my qubit. So on the North Pole is kind of 1, on the South Pole is 0, and I'm a little bit closer, and you also a little bit closer to the North Pole. So there is a little bit more chance if someone will measure us, if we would be on the surface of the qubit, then if someone would measure us, we would more likely be kind of on the North Pole or in the 0 state.
The 1. Oh, 0 is up and 1 is down. Okay.
Yeah, 0 is on top. Let's come back to this. So 0 is on top, and the sorry. 1 is on top and 0 is on bottom. So if someone would measure us, then we would more likely to be kind of in 1. So I'm sorry if I said that wrong.
Okay, no worries. It's okay.
Okay, so like another example, if you would be somewhere in the Ecuador and someone would measure us, then there would be like the same 50% chance to be measured in the again like one state or the 0 state. So 1 is on top and 0 is on bottom. So would be the same chance that we get to the 1 or to the 0. So there is like super cool features of those qubits, because there is possible to do such a things that are not possible to do in classical computers. Like, for example, if we could take 2 qubits, then we could entangle them, and entanglement means that qubits get synchronized. Basically, if we kind of, for example, if we met somewhere in Mexico City, and we take 2 qubits, and 1 qubit will go with you and another qubit will go with me. So we would kind of synchronize them, and then I fly back to Cancun, and then you kind of decide to change the state of your qubit, like the kind of, let's say you could put it to some different position here. And then position of my qubit will also change, and it kind of doesn't matter how close or how far we are from each other. So the qubits kind of get entangled or synchronized in other ways, in other words. And then this allows us to create some kind of unique algorithms for quantum teleportation of information, or kind of do some kind of do very, very interesting things. And actually the quantum communication is much more secure than just a classical communication, because if kind of some eavesdropper or kind of some listener would kind of join our conversation, he can just kind of listen us and we wouldn't know about it. But if we would use kind of quantum communication and someone try to listen our conversations, then we would surely know about it. So it's basically the quantum communication is much more secure.
Because basically, the only way to communicate between them is that you each of the persons have one qubit that is entangled to the other. So there's no way that any other qubit's gonna be that it's not entangled will show any information to any other one. Is that what it means?
Yes. So the thing is that because kind of those qubits are entangled with each other, so they kind of have the same state. And if kind of someone would try to kind of clone our qubit and have the same, and he try to understand what value does it have, he would need to measure it. But if he would measure it, it will become 0 and 1. And because it kind of becomes either 0 or 1, we also see kind of change in our system. Then if someone measure it, our qubits also kind of go to the 0 or 1 state. And we see that kind of something is kind of the qubits kind of change its states.
Okay.
Okay. So, all right, this is kind of a hypothetical experiment. It's a Schrödinger cat. I don't know, maybe you heard about it. Did you hear about it?
Yeah, I got.
So
because I got physics on the university, so we had the theoretical part of the Schrödinger's cat. If it's inside of the box, it's either alive or it's dead. It could be both at the same time.
yes.
Basically, it's not a concept, yeah.
Yes, good that you know about it, because we actually use this kind of principle. It's exactly what's going on in the quantum computation, because it's all about kind of quantum physics, quantum particles. So you know that if we kind of there is like a detector of the radioactivity, and it can be kind of measure the radioactive material with kind of some probability. So if we do not open the box, then we kind of that detector could kind of the detector could measure it or kind of do not measure it with kind of the same % chance. So basically, if we open the door of the box, then we find out the cat either dead or alive. But if we don't open the box, then kind of the cat is in the superposition. It's kind of alive and dead at the same time. So kind of the same is going on when we do the kind of quantum algorithms. All the qubits are kind of in superposition between kind of being dead and alive, between kind of being 0 and 1. And when we just measure it, then we kind of find out if cat is dead or alive, or if the qubit is kind of 0 or 1. So, and here is actually the example of the quantum computing algorithm. Let's kind of try to go to the simplest one. It's algorithm written in just four lines. And basically here we have a circuit. So each quantum computing algorithm can be represented in the graphical view. You can see it's like a super simple. Here on the input we have a qubit. That is, so we allocated one qubit and we put him in the kind of value of 0. So we start, it's in the 0 state. Then we apply the Hadamard gate, and Hadamard gate kind of moves the position of the qubit to this equator, like on Ecuador, or kind of on this picture we can see it like on the kind of just between the 0 and 1. So this is what Hadamard gate does. And then at the end, we kind of measure this qubit. So if we run this algorithm kind of many times, we would find out that it kind of gives us either 0 or 1 with kind of equal probability. So for now, it's kind of 0, but let's try to run it. 0. Now it's 1. Now it's 0.
It's 0.
Now it's 1, 0.
Because it plays into the superposition of 0 and 1 in the 11th line in your program. Okay, so it's only gonna be 1 and 0.
Yes, it's kind of with this HUD, kind of Hadamard gate, we put it to the kind of superposition with 50% chance of being measured as 1 or being measured as 0. So
yeah,
when we read it. So there is a kind of more complex quantum algorithms. So let's see, kind of this algorithm actually entangles the qubit. So it basically that kind of how to synchronize the two qubits with each other. So if we would kind of meet with you in Mexico City, we would have two qubits. We would apply the Hadamard gate that would kind of we just used this gate in the previous algorithm, so it kind of makes random. And then we apply CNOT gate. This is the second gate is CNOT, so it uses two qubits instead of one. And the meaning if kind of this qubit is measured as 1, then it turns another qubit to change its state. But if the first qubit is not 1, then the state of the second will not change. So basically, these two gates allow us to have the same value of both qubits. And then if I would go back to Cancun, and then you would change kind of value of your qubit, mine will also change. And then kind of at the end, we just measure those two qubits here. So we could run this algorithm. So we see kind of sometimes it's kind of 0, sometimes it's kind of 3.
0 and 3.
Yeah. 0, 3. So, but we kind of see kind of if you see on this on the circuit, if we have 1 on top, we always have 1 on bottom, or if we have kind of
because they're entangled. Okay.
Yeah, because they are entangled, they always have the same value. So this is kind of means that they are synchronized. So never different values. So, and then there is like some other kind of algorithms that are kind of maybe more complex. Let's try to see this one. Maybe take some time to get it.
Yeah, because maybe it's compiling.
Sorry, what's again?
Maybe it's compiling part of the code, so
good assumption. This doesn't need compiling, but maybe something wrong with this website at this moment. So let's just take another. It's kind of the website for two examples, but we would come to kind of idea of using kind of the professional kind of cloud services for quantum computing. So this is just kind of another example. I would just, like kind of show maybe different examples just to have some sense about like what kind of quantum algorithms could be. So this is kind of this does inversion of quantum Fourier transform. So you already see kind of many gates, some kind of swaps, some CNOTs, and kind of already kind of much more getting much more complex. This also like algorithm on kind of many qubits, just kind of let's see about this.
This sample takes a while to run.
So yeah, basically it needs more time to get it.
Yeah.
Right. I just restart. So
basically, it's that one. What I saw is basically it's taking position of the position of the superposition of the qubits, so it can represent colors. That was interesting. Okay.
So the colors is just a way to represent information, because kind of qubits can be kind of rotated around kind of y-axis or z-axis or kind of x-axis. There is like 3 axes, and they can do rotation around those. So basically all the gates, they kind of just move the qubit from like one position to another position. And like this algorithm is part of the Shor algorithm, and Shor algorithm is that algorithm that would allow to actually kind of decrypt any kind of information without knowing its kind of public or private keys. So it's basically with this Shor algorithm, the kind of someone who will create sufficiently powerful quantum computer could get all the information in the world. So basically this kind of thing. And yeah, let's move to this to the next one. And here is another kind of example. I just want to show you kind of something more complex, and this kind of website have some kind of dynamics how it works. So basically this is also kind of quantum Fourier transform that kind of it is used in the Shor's algorithm that we just talked about, and also it is used in music. It is used in kind of different kind of encoding, decoding. So, and then it basically changes the values of those qubits. We have a kind of 8 qubits as the inputs. They are kind of set into 0, but this thing actually changes the state of them. And then because we kind of have this kind of H gate, S gate, T gate, kind of different gates, then we able to kind of move the basis of computation to kind of its basis based on frequencies. So as you can see, this kind of qubit on top, it makes the rotation kind of in very slow pace, but the second one is already faster, but also kind of doing the same kind of rotation, but faster. And then it's more faster and faster. So it's basically kind of allow us to kind of to see how the quantum computing algorithm can be made. There are also kind of some other examples, superdense coding, for example. This algorithm allow us to send the information, but kind of if we would send 1 bit of information with classical computer, then we would receive kind of 1 bit of information on the other side. But quantum computing allow us to be kind of more efficient in sending information. So if we would send 1 qubit, we can transfer 2 bits of information. So if we send a qubit, we would not just get 1 bit of information, but we actually can get 2 classical bits of information. So and this kind of super dense coding algorithm allows us to kind of to send 2 classical bits of information and code them in just 1 qubit, and then receive those 2 classical bits of information on the end.
Okay.
All right. So here is example how like what could be done with quantum computing, or like how could we process data. Like for example, if we would do some like let's say financial analysis, we could have kind of a lot of data, maybe from the stock exchange, or maybe kind of could be kind of various kind of financial data. And then we would extract them, we would pre-process them, and then we could kind of encode them as a quantum bits or qubits, and then we would run those kind of algorithms that we was just looking at. So that quantum algorithm would allow us to kind of to solve some financial problem, maybe for portfolio optimization, or maybe for kind of quantum machine learning algorithm for predicting stock, or maybe detecting the fraud, or kind of doing kind of some other kind of problem solving with the financial data. on this slide, I just want to show what are the needs in the quantum computing industry. And kind of basically, quantum computing is just very rapidly developing field. It's very new. It's kind of one of the most new industries and one of the most powerful machines that can be kind of done. And then this industry needs kind of various kind of chemists, physicists, mathematicians, scientists, technicians, engineers, kind of, and a lot. And one of those who are the most needed in this industry is the applications and solutions architect for quantum kind of solutions, and also quantum algorithm developer. And the quantum algorithm developer exactly do what we just saw here. So kind of he creates those kind of quantum circuits, and he writes the quantum code, and he kind of do all these wonderful things. And interesting things that there are different technologies available to write a code for quantum algorithms. There is like a Qiskit from IBM. It's a Python library. There is an open assembler. It's OpenQ assembler. I mean OpenCASM. That is like assembler, but for quantum. There is Q#. It's a special programming language.
Basically C#, but in quantum.
Yeah, basically like a C#, but for quantum algorithms. So it's also was created by Microsoft, like C#. So, and the Circ is a library from Python for Python from Google. Also good luck. The Qiskit is from IBM, also library. So now we come to this idea of desktop quantum computer. So it's kind of very new thing, and basically some Chinese company came up with a very small. I mean that it has just 2 qubits, and it cost about $5,000. It's kind of super cool things to see, but it's not something that kind of any company would use. It's rather for maybe for entertainment or for some special kind of tasks. So the kind of personal quantum computers are not here for now. So they just regular people wouldn't have kind of quantum laptop at this moment. Maybe in future they will come up. For now, kind of companies and people, they use quantum, basically cloud services for quantum computing. And this is example of IBM quantum cloud service. So what the algorithms that we saw before, one like this or those like we see here, they can be also launched here. Here. So as you can see, we have like 4 qubits here, but it's actually we can have any amount of qubits that quantum processor allows us to do. So we have all those gates, so we can put them on the circuit. So we can either write code. If you can see, if I put some gate on the circuit, then I also get a code in this code editor. Or I can just write the code, and then also the circuit would change. So like okay, now I'm in read-only mode, but yeah, it's possible to write. I need to sign in for writing the code.
Yeah.
So it's possible to write it. And then also another service, it's Amazon Braket. It also allows to do quantum computing in cloud. It works in a similar ways like the one from IBM. Also Microsoft and Google, they have their cloud services for quantum computing. And then they provide access to quantum computers of different companies like IonQ, Xanadu, Rigetti, and also kind of IBM services and kind of many companies that create their quantum computers at this moment. So this is a Qiskit. This is kind of one of the best libraries for programming the quantum computer. And this is what kind of exactly this code that we could write here. This is just kind of a website for this library. They have kind of nice documentation, and they explain how to write the quantum algorithms. And here we can find the compatibilities with various kind of quantum computing hardware providers. You can see like there is many companies. This IonQ that I already mentioned, Azure Quantum, this is from Microsoft, Amazon
From
Braket.
Microsoft, yeah.
Yeah, from Microsoft. So IBM and kind of NVIDIA, Quantinuum, Rigetti, Strangeworks, so kind of many quantum computing hardware providers. So it's compatible with all of them. This is Circ. It's another library from Google. They have a quantum AI team. We actually started with going to their lab, kind of when we started this presentation. So they created their own kind of library, but it's basically allowed to do all the same things that we could do with Qiskit, just kind of using another one. And then this kind of website for OpenQASM, it's a kind of quantum assembler. Also, kind of they have documents how to write all this, so it's possible to just take a look how to define qubits, how to kind of use different kind of type of data, and so very kind of.
It's funny. It looks simple. It looks kind of simple. It looks mostly like C# on most of the part.
Yeah, exactly, like C# or like C in general. So
yeah,
like it's more low-level language. Those Python libraries more high-level languages, and this is. But good news that no matter on what language we write it, it's always possible to convert the code from one language or one library to another one. And basically there is a company like this one. It's called Quantinuum. They created very good library, and it's good because it's basically allow us to write a code for quantum computing and then convert it to code on other programming languages or on other platform. And also it kind of allows us to write one code and run also on other hardware. It's kind of already not doesn't matter like what technology we use or what programming languages or library do we use for writing the code. The good news is that just kind of it's all convertible, so kind of simplify our life. Here I just want to show the IBM roadmap, and we are kind of somewhere in the year of 2023, and in this year they wanted to come up with a Condor processor with more than 1,000 qubit. So I think it's not down, so I haven't heard that they created it yet, but they have some plans. The most powerful quantum processor is 433 qubits, and it's like already enough to run very complex algorithms. So it's kind of a good number, but not enough to run Shor algorithm yet. So kind of many companies have just, like a few qubits. Like some company, some startup recently started, they had a processor for 2 qubits, then they created a processor for 10 qubits, and 433 qubits is kind of already a lot. There is a D-Wave company, D-Wave, and then they created a quantum processor with 5,000 qubits, but it is more than anyone else have on the market for sure, but they are not completely quantum computers. They also use the qubits. They also have kind of those. It's possible to run algorithms on their processor, but they don't have gate model, so they don't allow to run circuits like this. But it's possible to solve problems like optimization problems for financial markets and for drug discovery, material design, for logistics. So this is kind of adiabatic quantum computer, and this company that actually started the first. It was one of the first companies that started to create the quantum computer. But their computer. Their computer doesn't satisfy the Di Vincenzo criteria. There is a kind of criteria. That defines what is a good quantum computer. So those kind of 5 criteria and 2 additional ones. They kind of say that good quantum computer should have a scalable physical system with well-characterized qubit. They have ability to initialize the state of the qubit in the simple state, kind of they define it like a 0 or 1, and then they would have long relevant decoherence time. The decoherence means it's a time when the qubit kind of forgets its value. If we kind of leave the qubit for a long time, then we come back and then find out that qubit is not in the same time anymore. So it's kind of the scientists are thinking how to make this long decoherence time. And also the kind of important criteria is that universal set of quantum gates, and this is why the quantum computer of D-Wave, this with 5,000 qubit, they doesn't satisfy this criteria. They don't have this quantum gate.
So they have their own proprietary gates, basically.
They don't use a gate model at all. They kind of, it's possible to define the kind of some algorithm like a mathematical formula, like define constraints, define different characteristics of that algorithm, but not possible to make this kind of circuit. So, and then they have kind of qubit-specific measurement capability. That means that we can measure qubit and find out if it's in the 0 state or in the state of 1. So those are the most important criteria of the quantum computing. And then here is another lab, just kind of to make some sense about kind of what how they do develop those quantum computing hardware, and then
it's crazy, but basically it's a building mostly for cooling because they need to be like in superconduction state.
right.
I understand. So they need to be basically almost in absolute zero, as you said at the beginning. So that's the biggest problem that we have right now with the quantum computer.
Correct. They need to create this kind of dilution refrigerator, and this is kind of exactly the laboratory in which they build this quantum computer. So it is not done yet, but this will be put into this dilution refrigerator and cool it down to kind of almost 0 to have this kind of supercomputing, kind of superconducting features.
That's like what I got about. But that's why they were so excited about this new material that supposedly was a superconductor at room temperature. What that was not true at the end.
Yeah,
I understand why.
Yeah, LK999, I think. So yeah, but even though it's kind of it doesn't allow us to have superconducting features on the room temperature, there is some technologies that actually allow us to do the quantum computing and the room temperature, and I think those kind of photonic quantum computers, they don't need this superconducting. They're based on photons.
They just light, basically.
Yes, basically on light. They use light for the computation. Let's see, we can have a good image here. Yeah, this is so kind of send lights, and then they don't need to cool it down. So also, some people already create memories that like a quantum memory that doesn't need to be in those 0 temperatures. So it also can quantum memory can work in the room temperatures. So here is like another scheme of the photonic quantum processor. So it's kind of
also interesting
technology. Yeah, super cool what they do. And then let's see, here is a lab. It's a Berkeley lab for kind of, I think they collaborate with MIT. So they have clean room, the laboratory itself. It's like a lot of different hardware. They kind of create those devices. They do all those kind of communications. They kind of, and it's kind of many people work here at the same time. So
yeah, networking and everything they need to do.
Sorry, once again.
Networking basically, and that's basically the computer in there.
Yeah, networking, signal processing, because kind of what everyone shows, kind of what all those companies shows is what is inside of the dilution refrigerator, and they show their schemes for quantum processor. But what they kind of almost often hide is that kind of this devices that actually sends the signals to the quantum processor, and this could be kind of very secret information, and companies do not like to share that. So
yeah,
then they created here kind of another quantum computer already kind of assembled here. Oh, kind of looks cool.
yeah, basically it's a full lab.
This is kind of a platform that kind of allows to run Jupyter notebooks. So kind of Jupyter is kind of I don't know if you're familiar with that, but if you kind of ever had experience with Python programming languages, or maybe you will have in future, then kind of they like kind of different scientists and data analysts, they like to run the code in the Jupyter notebooks. So it's basically they allow to kind of write some text and let's see, maybe we can have, yeah, basically here is one example of that Jupyter notebook. And then they could write a quantum computing code inside of that, and it allows kind of to show different graphs and circuits and put the text. So kind of cool way of showing the information. And this platform, they allow to run those Jupyter notebooks somewhere in the cloud. So kind of you don't need to run it on your local computer, but kind of if you want, you can. It's just kind of a thing that kind of allow you to access from anywhere to those Jupyter notebooks, and it has access to various quantum hardware. Mm-hmm. So here is actually the difference between various modalities for those quantum computing. So
Qubits, okay.
Yeah, like how do they implement those qubits? So one of the leading modalities that's superconducting, the processor we saw in the beginning from Google. So you see the Google Rigetti, Oxford Quantum Circuits, IQM, IBM Quantum. Many other companies, they just create the qubits on superconducting. Then trapped ions like IonQ, Quantinum, and others like IQT also. Then also they use photonics to create the quantum hardware, kind of Xanadu, PsiQuantum, and others. Like they also use neural atoms, Q-era, silicon spin, and quantum dots. Also kind of interesting technology. The quantum brilliance and silicon. So the quantum brilliance is actually a company that takes the real diamonds, and then they kind of explore where are those kind of silicon or the quantum dots, where they are located inside of the brilliant, and then they use real kind of particles trapped inside of those brilliants to do actual computation. So that's kind of another interesting aspect. So All right, here is just this is a kind of interesting video. It's about how they apply quantum computing for music. And then, as you can see on the screen, they have these qubits. So here's the professor who created it. Then
is what we are, giving a glimpse of what is to come.
By the way, do you hear the sound when I run the video?
I can play video later after this. I have my second monitor. Wow.
I just sent
sound of qubits. I just subscribed to the channel already.
So it's kind of interesting approach because if you like, let's see, maybe we can find it here. I think it was, yeah, here on the finger, he has a kind of device. It's not possible to see it. Yeah, this one, you see on the finger, he has a device that allows to set the qubits in any state. And then when he kind of moves the finger, he also kind of change the music. So kind of when he just move his finger, then the value of this qubit change, and it basically change how the music sounds. So he called it kind of sounding qubits. And this is a kind of super cool project of quantum music. I show it to everyone who is interested. They also have paper about how they used quantum machine learning to train the algorithm that learns this music, and then it kind of creates more of that kind of classical. It sounds like a classical music. So I also send you link. So it's probably, if I try to make it sound now, you probably would not hear. But if you like, you can listen it maybe later. So I think we are kind of almost at the end of our lecture. Let's just kind of try to make some conclusion and go through what we covered today. Basically, the countries invest a lot of money, kind of a lot. They make a lot of investment into the quantum computing. We saw the Google Quantum Laboratory, and we saw how they create their kind of quantum processor. We talk about that quantum computing is needed for the kind of problems that take a lot of years to compute on classical computers. And there are many applications, including like financial services and logistics, cryptography, and many others. And then they use the quantum computing for
financial.
Right. For analyzing financial data and building the perfect portfolio for detecting fraud. And for here we talk about what was the difference between kind of classical bit and quantum bit or qubit. So it's possible to entangle bit, and then we have kind of various interesting effects. So kind of something like a cat of Schrödinger. Here we see various kind of quantum algorithms. I will send you this link. It's kind of interesting to watch. Also, I will send you this paper just kind of in case.
Thank you.
Would like to take a look on that, or maybe show it to someone. So we talk about these quantum algorithms, various technologies, various programming languages and libraries for creating quantum code.
I see that you are using Discord as well. Is there any interesting server in Discord that they talk about quantum computing?
Oh yeah, exactly. Look, here I have the Wumanium quantum program. It's basically the Discord channel for this program. There is kind of various topics about kind of quantum sensing, quantum software boot camps, quantum hardware, different quantum projects, also opportunities for entrepreneurs, research papers, and kind of a lot of cool stuff they discuss. So basically, it's a Discord channel for this program in which I study right now. So I send you link on their program. I don't know how to send it on the Discord channel.
I can say I can check it right now. I have like 3 monitors at the moment, so let me check. I'm opening in the other one. Explore communities is.
So yeah, I guess you can kind of join this this Discord channel. What as I see, the program is already most part of the program done, but the people join kind of every day. Even today, even today, someone joined the Discord channel. I don't know if it's possible to share the link on that.
I cannot find Romanian Quantum.
Okay, let me see.
Cover. If you put invite people right there, what it says invite people below there.
I see. So, and how do I invite?
Maybe you need the privileges of the.
To add a friend to
Invites are disabled. Okay.
Permission to help.
Okay.
Basically, the organizers could invite, but I would just suggest you to go to this site, it's like Womanium Quantum Program. I think I already sent you the link.
Maybe it's inside of the
and then you can register, and then they allow you to kind of to join this Discord channel.
Okay.
Also, kind of just in case, I want to share with you that now they also do the astrobiology program, and it's about like sending missions to some other planets and moons of other planets. Astrobiology. Kind of, if you like to join, just in case, it would be cool. Let's see. Here they have another program. But there is like important deadline on this Saturday or kind of tomorrow. They need to close the team. So if you kind of join today and quickly find the team, then you will have a chance to participate in the competition. I also send you the link, so just in case you can take a look and decide.
Okay. I'm enrolling right now in the one in the Women in Quantum enrollment form. Checking that one out.
Cool. I think the next time they will do this program, it will be kind of next summer, because last time it was kind of previous year. I didn't participate, but I knew about it, and this year I participated. So I guess, and this is like very, very interesting. A lot of speakers, a lot of interesting materials. Many companies do their presentations and kind of show their quantum technology. So it was nice. So also we talk about this quantum algorithm, about how do we process the data and use the quantum algorithms for analyzing the data. The need for professionals in the kind of quantum industry, some hardware that is available. So mostly it is the quantum clouds of kind of big companies such as IBM, Microsoft, Google, Amazon, and then some kind of libraries, the roadmap, the tour. Also, I will send you a link to this. It's nice tour to take a look. All right, and this also the Google one. So modalities for quantum, they all have their pros and cons, and the quantum music. So I think that's it. Maybe you have some questions.
No, basically what you just sent me, and right now with the with the Woman Quantum enrollment plan.
Huh?
There's a lot that right now I got information about how I can. I didn't know about how you can program into the quantum computer. You just show me some of those materials, so I understand it now. Why it helps a lot is because I'm right now studying at university right now in college. I'm exactly doing that in software engineering and networking. So I mostly understand because I'm almost like it's just 9 months to go. So I understand most of the code and everything that I just saw. So I had major understanding on those things. So because of course, part of my program has to do with future technologies. It's one of the things that we had. So I understand mostly how quantum computer works, but I didn't know how they program them or about the gates and all of those new technology you showed me, like the photonic ones and the one with silicon. That's really interesting. So I really appreciate that kind of information because those are the things that I like to see. Mostly on the on the how it works, I think I have to understand it.
Well, very nice. Thank you for this feedback. Maybe you have any ideas how could you kind of use quantum computing kind of in your life, like what you can do with it?
Mostly on my life, the way that I'm doing stuff at the moment is like first of all, as a feedback for this, I think it's better to focus on possibilities on how to use this, because let's say it's not you're telling this to another person that is not me, that doesn't have kind of an understanding of these kind of technologies and how they work. Any other person might have a problem on understanding. So why do we need this? On my case, it's not that because basically I did have the course of part of my university. One of the things that I had to do is future technologies. On how I will use it, mostly right now, I'm more focused on telecommunications, basically with the quantum entanglement. That's really something that I looked at. It's really cool. Mostly because we are right now, let's say, one of the biggest problems that we have right now in telecommunications basically is the lag. This lag that is represented by the speed of light through the networking systems and all that. Usually that stop us to have a really cool technologies. So mostly remote technologies. So I see this as a possibility to eliminate basically the ping, like the milliseconds that you have between communication from me to you. Like right now, I am talking, but you're receiving my voice basically like tenth of a second delayed after I talk, and that side works basically nothing. Tenth of a second is not much if we are talking or looking at each other, or maybe sending a document. But there are really a lot of applications that they need real time communication that we right now don't have that kind of systems right now that are working or available, so we can have real time communication. So basically, what I would use quantum computer is not networking to eliminate those kind of delays on the networking communication.
If kind of is it possible eliminate the delay or not? It's basically the topic of the research at this time, and I actually read that kind of the quantum communication would not allow you to kind of to be faster than the speed of light, because anyway, if they kind of you have the synchronized or entangled qubits and you change one of them, then kind of you can get it probably exactly at the same time. Or well, I don't exactly remember. I don't exactly remember the experiment that they did, but they came to conclusion that this kind of speed of light is still important in the quantum communication, and it's kind of.
Yeah. I'm basically, because of physics, I understand what you said, but anyway, it's like, for example, I understand that it doesn't matter. There's not. It's not affected by the medium. By that I mean is like, right now the problem with the speed of our communications is supposedly they work at the speed of light, supposedly. But we are right now. Let's say that the Zoom server that is between us is in Mexico City, or in Merida in Yucatan. So anyway, I can bet that our communication is delayed by 120 something milliseconds at the least, and that is because. But if we send one photon from where I am to where you are, it's not gonna be 125 milliseconds. It should be less than that, like not even 1 millisecond. So the problem that I see here is the speed of light is affected by the medium as well. So right now our medium is basically glass, like with fiber optics, and also some copper and other elements like gold, copper, and all of those. They do slow the speed of light at some point, and also the processing that is happening between the servers to communicate ourselves, our computers, and all that. All those delays, they don't let us to have real-time communication. I know the real-time communication, it's not possible because of physics, but at least way better than we have right now. That's what I mean.
Yeah. Surely the quantum communication would make it faster. So kind of how they explain those kind of entanglement is that kind of if some particle change its characteristics, the other particle should change those characteristics immediately. So kind of on one hand, it should work faster. At least there is no wires and there is no kind of I don't know how they call it. Yeah, kind of no communication or cable or something like this. They can kind of have one qubit on the satellite, for example, and another qubit on the Earth. So kind of there is no medium for that. On the other hand, there was like some information in this course from MIT on quantum computing, and then they describe it that kind of the quantum communication may need some medium, and they kind of described some kind of technology for that kind. And they also described that kind of experiment. I maybe need to refresh how they did that experiment, and then there was like was super interesting, but they came to conclusion that the speed of light still matters for kind of transferring the information between kind of particles, even if we don't need the wires, or even if we don't need kind of any kind of medium for that. So I would rather kind of leave this kind of like an open question. So I kind of do not have the perfect answer for this right now, but this is something that kind of it would be interesting to research and actually find out how it really works. So kind of just can't answer on this right now.
Yeah, no, that's okay. It's fine. Like anyway, what I just learned today is that there's that possibility. Like in quantum entanglement, I understand that just to research more on how the medium works, but for sure it has to be better than the thing that we have right now.
Absolutely, it's kind of it will be faster, it will be more secure, and there is like a field of quantum communication. So it basically that field has a lot of interesting concepts to learn, like what is quantum, not communication. And then there is also kind of many organizations and the startups who kind of create communication. And I know some banks implemented this secure quantum communication to kind of to do exchange of the information. And then there is they have a quantum key distribution algorithm to make the quantum communication secure. So the quantum is much more secure than just a classical communication. And the quantum key distribution is algorithm that those kind of banks like I know Wells Fargo or Morgan Chase, or actually some banks in Europe, in China, they actually do this quantum communication between them. So on one hand, they allow to find out if somebody listen or not. On the other hand, it's just much more secure, and it's not kind of not possible to attack it with the short algorithm. They kind of this professor created the algorithm that would allow to decrypt any information, but the quantum communication could be kind of doesn't have that problem. So even if they get all the information in the world, the information that is kind of that is passed with the quantum communication, it will be kind of secured. So yeah, and then they use those quantum communication between kind of satellites, between Earth, between various organizations. And I know that in New York, they already started to build the quantum internet. They kind of built, I don't know, like about 40 or 50 kilometers of that quantum internet. And basically it's, I think either they already connected or they are going to connect this quantum internet to the stock exchange, and then it would allow for more rapid communication with the stock exchange. Like those high frequency trading will become even more high frequency. So kind of cool thing.
Yeah, that's exactly what I was thinking. To answer your question, exactly, they are doing it already, but yes, that's exactly what I would use for me. It's mostly in communications. Because in any other area right now in my day-to-day life, I don't see any other applications right now. Like I understand there are endless possibilities, but I right now my biggest problem is telecommunications, real-time telecommunications, or close to real-time communication.
So you kind of work with the communication kind of at this moment.
No, there are some applications that I have already two patents. And some of the problems that I have mostly with those patents to bring them over to life is basically it's the speed of the network at the moment, or how entanglement is how much things are happening in the network telecommunications that are right now happening. Like even though we have fiber optics through the ocean and all of that, our biggest problem right now is the servers. Like how they process the information inside of the server, and the time that my computer takes to send information. Then it goes through my router, and then it goes to the server of my ISP, then to the server of the company that I just requested the information. All of those steps is basically, it doesn't matter if you have like a highway without speed limit and 30 lanes. If you put stoplights every 30 meters, like it doesn't matter. You're gonna be slow anyway. So that's the problem that I have right now with my patents.
Okay, interesting. And on this picture, I especially opened it because it's a quantum internet in China, quantum communication network. So you can see it's kind of almost 5,000 kilometers or 4,600 kilometers across the country. And then they use kind of 70 optical fibers on the ground and to ground to satellite links. I think this is the biggest quantum internet or kind of quantum network at this
Interesting.
point. Yes, super cool.
I will research that because that is something that really interests me right now. Basically, because I do have the patents, 2 patents right now, but I cannot develop them because of that.
Okay,
Maybe that helps.
What's your patents about?
They one of them is in medical field, and the other one is basically on the telecommunication field.
Oh, cool. So, is it something about algorithms or kind of some applications or?
Mostly applications. The medical field is mostly is an application, and is mostly for people that have disabilities. And the one in telecommunications is mostly for well, it has to do with not with finance per se, but there are some features that it's adding features to existing already applications that we have, so they can help us to work even better.
Oh, okay. Well, interesting. Interesting that you have a kind of patent for medical kind of thing for people with disability, because I kind of recently tried to launch a startup that would kind of allow ability to speak with any site, like you would speak with Siri or kind of. So this was a platform. It was kind of, I was thinking to make it like for people, to help people with disabilities to access any kind of website in the world. At the same time, I kind of didn't figure out the perfect product market fit, and there was not kind of sufficiently large market for this kind of platform. So I kind of just inform you. So
Yeah, I didn't get into Vuex like see what they offer, but is very similar on what I'm trying to do. So there, in part of my pattern has applications that are similar to what Vuex is doing.
Oh,
I had to do my research before I of course I applied the patent for my patent. So of course I had to do my research on to see if nobody has already something that I am already trying to patent, because if not, it's an infringement. So I did research, and Vuex came to, of course, the one of the names that came forward. But when I applied them, we have several key differences on the way we work. That they have features that might help, or I may be able to use Vuex with my application. But that's something for later. The problem right now, it's because it's medical grade. We are if because of the medical grade and because it requires medical grade things usually for this application required that some of the elements don't have this problem with the communication. Basically, between one of them is interference. So the FCC, because of the FCC, they require some applications to have. Of course, they have to accept interference because of that's how the policies are. But because of the medical grade of this application, I should not be able. This should not happen. But the problem with the actual communication protocols that we have, we don't. It's not secure enough and fast enough. So there are some problems right there. So they need to be solved.
Okay, I think I understand. And this is actually the quantum communication would probably solve this problem. There is quantum key distribution. Basically, quantum key distribution allows to kind of create a key that you would use for symmetric cryptography. Kind of you would kind of with the same key you would kind of encode information on one side and decode on another side, but quantum key distribution allows you to kind of distribute this key kind of in real time, and this kind of this explains how does this work. And then kind of if somebody is listening and if there is some eavesdropper that could just kind of like to kind of listen the channel, then it is possible to find out if kind of if somebody listening or not. And then there is like various protocols for this quantum key distribution. So
that's interesting.
That's what some of the most innovative banks who already started to use the quantum cryptography use. So I think those in Beijing, as we just saw in the map, they build this for distributing the keys and making all this kind of communication secure.
With that, well, that's something that that for sure I will research, but because yes, that's exactly what the main topic that they piqued my interest on these quantum technologies right now for telecommunications.
Yeah, it's maybe kind of too early. You basically need the quantum network for this for distributing the keys, because you kind of send the qubits. So if you kind of don't have it in your city, if you would be in Beijing or in Shanghai, then you could probably kind of join this network in some way. I don't know how they provide the access, but also good question to research. If in Mexico they probably do not have quantum,
yeah,
though kind of some company wants to invest also about $1 billion in Mexican quantum technologies. But
basically what I think that it will have, because also it's because of the hardware required to do this. It's mostly like I know that there are limitations on what I want to do on this patent. It's already there, so I know that I don't have the technology right now and available to the public to launch this. But as I see in right now is that this is not something that is too far off, and also I can still develop over on this. So that's this information is really valuable for me on that part, of course.
Cool. So if you don't need kind of immediate solutions that you need to kind of implement already today or yesterday, then kind of I think several more years and we will get kind of there. So it will definitely will be developed more and more in kind of all the parts of the planet. So maybe kind of in 5-10 years we could get something like this in Mexico or kind of in other countries, and then would be kind of more secure to kind of would be better to think about it in like a solution for the long term.
It's more than a solution is it's the only way that it could work as I see, or if there is a really big advancement on our existing network, but it's not something that keeps me up at night because I already have the patent, so I know they cannot steal that from me. It's already registered to my name. So but yeah,
registered and so it's yours.
Yeah, it's mine. Like it's not something that is keeping me up at night. Somebody will take that from me. Like, and if somebody comes with that, of course they will have to call me or. Yeah, and there might be also labs or some other companies that might be interested in this kind of technologies to develop it, and they will put the funds and all that. So, but it's good to know that there are these other options, or also so to circumvent the problems that I have right now to deploy this.
Right. Yeah. If they kind of need to use your patents, they will need the license from you, kind of for doing that. Yeah. Anyway. All right. Maybe kind of you have any other questions or something else you would like to discuss?
No, I'm fine. In fact, I need to go to. So they're waiting for me to go to eat. But thank you very much. Really, I really appreciate all the information that you just gave me. Like, this is something that I know that I will have. I have a lot to think now. I already enrolled into the Womanium website.
Yeah.
So and I will read most of the documents that you. Oh, not most. I think I will read all of the documents that you just sent me. So
nice.
I will see what else I can come up to. But I thank you very much, Artem, with all this information. I don't know if there's anything I can do for you, or if there's anything else you need from me.
I don't know, just kind of, it was, for me, it was just nice to talk to you today. It was kind of nice to meet you. And so cool that you kind of, that you dedicated kind of so much of your time and attention to kind of learning more about the kind of quantum technologies. And so I kind of, I appreciate kind of attending this session today. And if you would have kind of any questions about maybe kind of some topics that we covered, or kind of any other topics in kind of software engineering or maybe in entrepreneurship, then kind of feel free to reach out, and we could continue our conversation.
Of course, Artem. I'll have you already in my contacts. Thank you very much.
Hey, thanks to you, and have a great weekend.
Thank you. Same to you. Bye.
Thanks. Bye.
Bye-bye.
Bye.